I think it's a good time to get started. Thank you everyone for coming. Today we're very happy to welcome back a former student of Imperia. Marta Garnelo was a PhD not so long ago. She has been since then, she's now a senior research scientist at Google DeepMind. She has done a lot of very cool stuff on multi-agent research, generative models, and yeah, the latest thing that she's going to be telling us about today. And we are looking forward to hear what she has to say. One thing though, for those of you who are here for the first time, ICARL is a seminar series on reinforcement learning. We are very happy to be sponsored by InstaDeep and Google DeepMind. So for those of you in person, we'll have some networking with food afterwards. You will be able to ask some questions to Marta if you want as well, although you can also ask on the go about the talk. And if you are online, please put your questions on the chat and we will read them out loud. So without any further ado, the stage is yours.
Thank you. Okay, hello everyone. My name is Marta. I have been a researcher for a while now at DeepMind, and today I'm going to be talking about the latest paper that we have published, and it might be the last one actually for a while now that we've moved on to language models. And it's the title of our paper, which is called Exploring the Space of KVQ Models with Intention, and this title will make sense by the end of this talk. This work was done jointly with the second person on that image, which is my colleague Wojtek, so big shout out to him as well. Before I start, I wanted to let everyone know that I like to do my talks relatively high level. I try to get everyone to understand what's going on. It's not going to be very technical. If you want nitty-gritty math, there's proofs in the paper, there's math, you can go and check it out there. But meanwhile, if anyone here has a question or is not understanding what I'm saying, please ask straight away. I'd like everyone to understand what's going on and not lose anyone in the process. So this project is a bit of a weird one. I've actually worked on RL in the past, which I know is what the seminar series is about. This project is not that much about RL, but I'm still going to pretend and try to squeeze it into something that could be RL eventually. The motivation was a bit differently. We looked at the machine learning landscape at the moment, and one model that very unquestionably stands in the center of it is attention and transformers. And if we look at any of the successes in recent years, there's always an attention mechanism somewhere in there. From protein construction to obviously image generation, as well as text generation, there's transformers and attention everywhere. So with this in mind, we set up on a project to see if we can develop a model that is similar in nature, but has different properties. And before I start talking about any of this, I wanted to get some nomenclature, so we're all on the same page about attention. I'm also going to initially give an overview about attention. Maybe you're already familiar with it, but if you're not, we'll go slowly from the beginning. So when it comes to what transformers and attention often do or are used for is this thing called few-shot learning, which used to be called meta-learning, which is now called in-context learning. There's loads of different names for it. And it's this type of task that is set up in this way. You're essentially at test time, so at inference time after you've trained, you're given a few things for classification, I should add. You are giving some examples. So for example, if we want to classify images of food, you would be given some examples of salads, burgers, what pasta looks like, and so on. And you're giving these example images. We're going to call them keys. And all of these examples have some labels that describe what they are. They are these colorful boxes, and they're called values. And then what you want is that given those examples, if you feed them to your model, you can ask them about a different image, which we're going to call query, and it should be able to predict the corresponding value for that query. So keys, values, queries, those are terms that are quite important for the rest of this talk. That's also why it's called KVQ Space. So important to remember. And predictions throughout the talk, because of the maths, usually are abbreviated with H, which is not that convenient, but just keep that in mind. So how does attention work more specifically? Okay, let me go back here. If we look at the model, we see that the model takes in K, V, and Q and just makes a prediction, okay? So how does the inside of that black box actually look like? It's very simple given how powerful it actually is. So we just have a bunch of computations that can be summarized with this math equation. It's just matrix multiplication and a softmax. That's all there is. And you output your prediction. And for those of you that like a visual representation as myself, really all you have to think about is you have your queries, which is, if you remember that image, for example, of the pizza that you were interested in, you compare it with all the keys, so all of the example images that you had, you have some sort of similarity matrix, you can think about it like this, and then you say, okay, given how similar my example is to all the other ones, let's weigh that with the values. So let's weigh it by the label. Are we all on board with attention? Does this kind of intuitively make sense? Good. Transformers are nothing much more fancy. They're basically just stacked attention. So that module that I just described to you, you essentially just take that with a bunch of residual connections, some layer norms here and there, and an MLP. And then that would be one transformer block, and you just stack those on top of each other. And that's literally most of what like ChatGPT and all of these models are, right? So it's really not that fancy if you look at the computational side of many of these things. However, there's something that makes these models very powerful, unquestionably. There's different theories as to why that might be. There's some research out there that shows that because attention allows for multiplicative interactions between the inputs, that brings out a lot of expressivity. If you think about regular deep neural networks, the inputs are just multiplied with the weights, but they're never multiplied with each other. Here, we're actually multiplying them with each other. This makes the class of functions that you can represent much richer. So that's one of the hypotheses. However, when we looked at this, we're like, okay, basically this input structure makes sense for in context learning, makes sense to have some reference values and then some queries that you want. And that's a computation, that's all fine. But what happens if we just do a different computation? Like attention wasn't God-given, right? Like we don't have to multiply the matrices in that particular way. There's a reason historically also why it's done like this. But the motivation for this project was to think, can we do something else that maybe gives us a certain benefit? And there's different ways to where we got. But one of the questions that we asked ourselves is there something that our current attention modules are lacking or cannot represent or do, right? And maybe we can gain on that. A caveat on this, it should be useful, right? There's many functions that are incredibly complex that attention is not going to be able to represent, but we also don't care about them. Are there useful computations that it cannot do? And we looked at this equation, and at the time I was actually working on optimization, which is where this somewhat random idea comes from. And one of the things that stood out to me is it cannot represent least squares linear regression, which it can, because, and I'll talk about it in a second. And at the time, and before I go into why, a quick refresher on least squares, in case people are not familiar with it. Least squares is basically where you're trying to regress your data and trying to find the optimal weights for your model that explains them linearly. What does this mean? If you have some observations, those pink points, and you have what normally is called X, but we're going to call them P's because that's what we're going to be calling them, and your Y's, which are values. You assume that your data is linear. This means you have a model that can explain how they're related to each other via lines. And more importantly, and what you want to do is you want to find that W, so essentially the slope of that line, those parameters. And the hope is that these parameters are then going to generalize. So if you can apply them to your queries, you will get predictions. I'm sure many of you know about linear regression. Here's a quick backup. This is a very simple optimization problem. You're basically just taking the errors of the actual values to what your line predicts, square that, add them all up, and then you say, okay, I want to minimize this. And if you've done optimization, you can do this via gradient descent. You can do Newton's method. But we're likely that this one actually very famously has a closed form solution. So you don't even need to do iterative optimization. You know that the best parameters are going to be the keys times your keys, and then transpose that, keys, invert that, and keys times values. Closed form solution. I'm going to show in this talk this equation a lot because we're going to use that computation in our new module. But specifically, I'm going to actually be using this down here. The reason for this, it's basically the same one, but we have an additional regularization parameter, which seems theoretical, but then when you're actually trying to compute a lot of inverses, you very quickly run into problems. So this just makes sure that you can take the inverse and that everyone's happy. But it's essentially the same equation. You're just adding a bit of weight on the diagonal of that covariance matrix. Okay, so we now know what least squares regression is. That's what the equation looks like. You can see that already by the fact that you're taking an inverse, there's no way that this matrix multiplication can approximate it. So straight out the gate, not approximate, sorry, represent. So mathematically, we cannot represent. Some of you might say, okay, That is a bit of a weird one to have selected of all the things. But if you look online, least squares regression is everywhere. This is me just Googling today, what do people say about linear regression and least squares? And from Harvard's Business Review to LinkedIn, Amazon website, ABM, everyone agrees that this is something that, believe it or not, is still used in the real world. It's uniformly used across sciences, right? And different applications. And it's still reliable to a certain point, and it's established. So this is a tool that is really used across industries. I especially like this towards data science, 3 reasons why you should use linear regression models instead of neural networks, to which this talk is the answer, why not both? So that one I liked. Okay, so fair enough. For me, we were aware of the power of linear regression at the time, but just to convince people, maybe why are we doing linear regression? So we know that attention definitely cannot represent linear regression. Okay. Can it at least approximate it? Right? Because if we have an approximator, then we don't really need a replacement. And anyone in this room that has dealt with deep learning will agree, yes, it should be able to approximate it. We always claim that neural networks, if they're deep enough, should be universal function approximators. So if you make your neural network very big, you should be able to approximate whatever function you want, which is fair enough. However, there's this question with everyone who works practically with anything in real life, can it approximate it efficiently? Because if I have to make a huge neural network just to be able to approximate it, as far as I'm concerned, it cannot really approximate it, right? We want it to scale somewhat decently. And so we did a little experiment to see if we were wasting our time or not. And it was a very easy one. We were just trying to train a model, a neural network with attention that can guess linear regression parameters. So it went the following way. Imagine you have the space of all linear functions. We're ignoring the bias for now, so just imagine it's just different slopes. I've plotted 6 of them here, but you can imagine they would cover the entire space. And then at each iteration, we would pick one of them, and we'd say, okay, this is a set of weights. On this slope, we would then select a few points. Those would be our observations. So we would have keys on the x and y's, our keys and values. And then we would feed these to our model and hope that it would predict our parameters. So that's relatively easy. And then at every training iteration, we would pick a new line, pick new samples, train our model, and hope that every time it predicts the weights. And a neural network should be able to learn this, right? What we wanted to see, however, is if you take the dimension of that regression, so what I was showing you with a line is 1D regression, right? So x is 1 dimension, y is 1 dimension. What happens if you increase the dimension of x, right? So all of a sudden we have 4, 5, 6 dimension of x. How big does your network have to be in order to accommodate and still have a low error in that prediction, right? As we increase the dimensionality of our problem. And that really tells you how efficient these models are. An MLP, which is the simplest neural network you can think of, very quickly, exponentially, once x is basically 4-dimensional, it very quickly doesn't scale very well at all. We're going to ignore neural processes. This talk is not about them. It's in peace. That used to be my previous research. Looking at the blue one, attention, it does well initially, but it also requires exponential amount of compute. So the numbers themselves don't actually matter. It's just showing that the scaling is awful. And all you're trying to do is predict, if I give you these points, what's the line that crosses, right? This is a very trivial problem that, again, as you saw from all these quotes, many people are trying to solve. So I think it's safe to say, can it approximate efficiently? It cannot. So this is where we got a bit excited. We were like, okay, here's a chance. There's something we could improve. We're not saying every problem can be tackled with linear regression. That's not the case. But definitely there is use out there. And it seems that attention, which is like the holy grail currently of machine learning, is at least not able to do that. So that was a good first step. So we thought, okay, what is a module that computes these least squares that we're so interested in? And so basically we just took, if you remember, that's the equation, that's the closed form solution for least squares. We just say, we're just going to take those computations and do them instead of the computations inside attention. You'll notice it's much bigger than attention. It's, however, not much bigger in parameter space. So you don't have a bigger network because the only parameters are those blue MLPs, right, which are shared across. So from a point of view of parameters, it's fine, it's the same. We have more matrix multiplications, which are those pink ones. That is true, although those can be parallelized. And most notably, the biggest difference is that we are having a matrix inverse. That's the yellow one as part of our computation. Now, matrix inverses, anyone that you talk to that has done linear algebra in computer science, they always immediately scare away because apparently they scale really bad and cubic and whatnot. we actually, as part of the paper, also have shown that computational complexity of our model is the same as that of attention. So I'll talk a little bit more about it later, but it's not as bad as we ourselves initially thought it would be. And because, well, famously we have attention, we call our model intention. Well, and so we then ran intention on this little experiment that I showed you earlier. That's the yellow line. And unsurprisingly, it did really well. It scaled linear. Now, obviously, this looks really good, but also this problem was exactly fitted to the computation that this thing can do, right? So this is not surprising. This was just a sanity check. Can it do that? Yes. So we can say intention can officially approximate, and not only that, it can represent least squares. So this was encouraging, but then we set ourselves out to explore other experiments, because so far this one experiment was incredibly toy and incredibly fitted to exactly our use case. So we went into the literature and we picked up, I don't know who here is familiar with the more old school machine and meta learning from 2017, 18. But back in the day, one of the main papers that did these kind of few-shot learning was MAML. And this was their first experiment. Like they started the paper and they were like, here, regression. MAML was an algorithm that would do gradient descents as part of their forward pass at inference time, and therefore adapt their answers in real time, so to speak, to whatever context you were giving it. And the way they were motivating us is very similar to the actual experiment that I showed earlier. They had the sine experiment where they were saying, okay, as an experiment, you're gonna sample a sine curve. So you sample the amplitude and you sample the frequency. On that sine curve, we're just gonna get a bunch of observations. Those are those points. And then we pass those observations as keys and values to our model. And we're also gonna pass some queries, which are just gonna be all of the places on the spectrum that we want it to predict the value. So that would be like those pink points, right? So you're saying, what does the function look like here, 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 and so on. And then for the next training iteration, you sample a different sine function, a different set of context points, blah, blah, blah. And so that was their experiment. And so we decided we implemented MAML, intention, attention, everything. Again, let's ignore neural processes for now. But if we look at the results after training, there were no big surprises there. We can see both MAML, attention, and intention. When there's fewer context points, you can see here there's only 4 of those circles, or net 4. Do a bit less well, and then the more you increase the context points, the better it does, because it has more information about what it's trying to regress. Well, you can see here already a little bit that intention does do better in the low context number regime, and we have quantitative measures. It's not just a cherry-picked example, but this was not very surprising. We were happy that it matched just the regular behavior of MAML and of attention, which were the other two we were comparing. What do you think? But what got actually interesting is when we looked at what happened with our models at initialization. So this was before we started training, like no weight has been updated in any of our models. And if you look at the results, attention does what you would expect. It's a neural network. It's going to ignore everything. It doesn't know how to deal with anything. MAML does something because it had these gradient updates that it has at test time, at inference time, are going to change the shape somewhat. So that's why it's not a dead straight line. Intention, the yellow, however, you can see it perfectly interpolates, and it's not been trained. This may look weird, and initially we were a bit freaked out, but it makes sense because, well, there is a theorem that says if you are in a space that is large enough, it doesn't matter what projection you have. You can have a random projection. You can still do linear regression on those points, right? And if you think about it, this is what is happening, right? We encode the points into some arbitrary latent space with MLPs, which at initialization is random. And then within that, we can interpolate between those points, because linear regression is going to work. There's always going to be a way of doing linear regression if the space is big enough, which is not only exciting for an interesting figure, but it shows that this is a very useful bias to build into our models, right? Like clearly this model has an this model can do regression before it's even trained, right? So we thought that this was actually very interesting. And the more context point it has, because it's good at interpolating, mind you, not extrapolating, it should be able to go in between points. And if you have enough like there, you're actually approximating the curve very well. And this is with 0 steps of training, which was really fun. Okay, so far, all of our examples have been on regression, and one could argue, okay, you're doing linear regression, so maybe it's a bit specific. So we decided to test it on other experiments, and we looked at classification. I don't know who is familiar with the mini ImageNet experiment, but basically it's another meta learning experiment that they had back in the day, where you would pick, you would have the mini ImageNet, the ImageNet data set, which are just small images from the real world. You would select n classes, and you would pick some examples of each. For example, here, some of orange, some of wood, I guess. And you would assign them any random label from 1 to n. And then that you would use that for that training run. In the next round, you would pick another set of 5 n images and also assign under labels, and then just ask, have them classify a few examples. And again, I'm not going to go into huge amounts of detail here, but intention, this is all very basic models. We implemented the same neural network structure behind all of them. No bells and whistles, there we go. And we optimized each to the best of their performance, and we still got intention to perform the best. It doesn't really matter if one is much better than the other. At that point, we were more about showing this actually works and it can be used for classification as well. There's a few more experiments that I think are interesting and showcase what we could be doing with intention. We had regression, few-shot regression. We have few-shot classification. And then we had the set of experiments where we had our model learn the remapping of certain points with a few examples. So what does this mean? We would sample some remapping, which is characterized by a matrix and some rotation and some shift. That would map points from one point in space to another. So you would imagine if you started out at the end of one of those lines, you would finish at the other. So that's just kind of twisting points in space. And so what we were saying is, okay, we're going to sample some remapping. Within that, we're going to apply it to a handful of points, maybe 5, apply it to them and show it to our model, and then have the model infer, okay, what would this remapping do to a different set of points, right? So you have to infer just from observing how they've moved, how others would move as well. And again, we actually, the intention is very good at something like this. Think about the fact that it is solving an optimization problem at test time, right? This is a power that the other ones don't have access to. You could argue MAML is doing some optimization, but it's only doing a few steps, whereas ours is doing the full computation of an optimization. And so you can see that's the mean squared error. So you want it to be as low as possible. And as we're training, intention goes down really quickly and also stays down compared to MLPs, which are obviously imaginably bad, but even attention does not do just as well. And the funny thing about this is when you're learning the remapping, it's not specific to something you've seen, right? So we did this, we have this cheeky figure in the paper where we just show a remapping of some points and then apply it to a whole bunny, you know, and you can do it. Even you show it 3 points and then you can have it rotate or move anything around that you want. Like it's generalizable to however many points because you've just learned the mapping, not just the individual points, if that makes sense. Finally, haha, the word policy. Okay, RL. So in the original MAML paper that I mentioned, there was also 2, I think, RL experiments. We're not as much RL people, but we originally tried to recreate, they had a navigation task where they would start in some point, have a target point, and then just some reward. The reward was just an exponential of the distance to your, the inverse of the distance to that point. We didn't have the time to do it proper RL in it. So what we call it is policy distillation, because basically we said, okay, we're going to have a model that given some observations, as if you had seen some observations from the environment, learns where is the target. And then the argument for this is that you could pass the knowledge, like if you know where the target is, you can condition a policy on this and it should probably help. I mean, you should be able to, famous last words, train a policy that given the target knows how to navigate there. We kind of split the thing. So this is how the setup went. We would sample a new environment at every round, which essentially meant you sample where the target is located in 2D space. And then based on that target, you would sample a few observations. So you would say, what's your reward if you end up here? What's your reward here, here, and here? So at those points, you just calculate what is the reward and what is the reward. And then you pass it to the model. And you say, okay, if you get the following rewards at these locations, where's the target? And then the model should be able to predict that little pink star. And we have some examples. Again, intention is really well. Again, unsurprisingly, this is an optimization problem as well. And for the keen observer, you will see that is a quadratic that we're optimizing, which again, least squares this is particularly well suited to. But overall, we are doing quantitatively much better. This is again the loss, so you want it to be as low as possible, and it's statistically significant. And then here's some examples of where the different models predict the targets are. So you want to be as close to that X as possible. And these little boxes are just zooms in the one at the top. So this is exciting. And for a group of reinforcement learning researchers, this could be the possibility of taking something and then, as I said, embedding this into an RL agent or having something that does the optimization and can tell you where to go next, or takes at least that part of the computation away. A final thing in terms of experiments, I have mentioned to you transformers, which are stacked attentions. So the natural question is what happens if we stack intention in the same way we would do it with attention. And we did this and we called them informers because intention informer. And applied this to one of the experiments that they also had applied in the transformers paper, I think, which was this task of outlier detector. So you would be given at every training iteration one of those rows of images where they're all the same except for one. So you have like the deer in the top one, and there's one of them is a plane, and then the model has to tell you which one of those is the outlier. And I'm not going to go into a lot of detail either, but this is just to show that it behaves as you would expect. So if you train for the transformer, obviously if you have only one of these transformer blocks, it will do worse than if you have 4 of these transformer blocks. And intention not only matches or is in the same ballpark, but then also has the same behavior, that as you stack, you're going to get increasingly better behavior, which ultimately is a lot of what the current transformers build on, right? That they're just massive and loads of parameters and training resources. Good. So this was the experiment. Is everyone on board with experiments model? Yay. One of the topics that was also interesting and that we talk a lot in the paper that I want to mention is the relationship between attention and intention, because this was something that we originally didn't start out with, but then slowly found out as we were researching it. And it turned out to be actually quite interesting because at the time where we were working on this, a paper came out, that's this one here, from also Google Research, that said that transformers learn in context by gradient descent. Okay, we'll unpack that in a second, but essentially it was looking at this model, which they called linear attention. Now, linear attention is very similar to the attention that I've shown you earlier. If you can see, it's just lacking that softmax. So it's the same, it's a little sigma that I have there. So it's the same computation as attention. It just doesn't have, if you remember, the attention has a softmax computation around the aquarium key matrix multiplication. So linear attention, very similar behavior, but mathematically a bit different. And that's, I think, why they went to this one. And their claim in this paper is that when transformers have one attention or one attention block or one transformer block, what this can be seen as is as doing the same thing as one step of gradient descent of least squares regression, which when this came out, we're like, this is a joke. This is literally very related to what we're doing. So essentially they're saying, okay, transformers are doing optimization of least squares, but one step at a time. So each block is doing one gradient step if you took the gradient descent approach that I mentioned earlier, rather than the closed form solution. So in this way, if you think about it, attention would be one step of gradient descent, and intention would be the closed form, all the steps until convergence, right? And so this to us was very interesting. And then we started looking at the equation a little bit closer. And if you remember, we have this regularization term, which also helps explain this. So if we, mind you, we have a rescaling of the query. So if we add this rescaling of the queries, which we're allowed to do, mathematically doesn't change anything. If we drag the rescaling of the queries into the inverse, you can see that we have two terms, basically, within the inverse. We have this covariance between the keys, but we also have what we call the regularizing term. Now, as alpha goes to infinity, this whole term with the rescaling, because this is going to divide, becomes the identity. So as alpha, as our regularization is really strong, we get back attention. And if we scale back the regularization to 0, we basically lose that second term and we get normal least squares. Okay, so all of this, what this is saying is that you can almost have a slider between attention and intention of how much when you use this regularization parameter. And which also a bit it makes sense if you think about this being one step versus several step, close from solution versus one step. And it's kind of explained by this intention attention, which we thought was really a really cute little thing. So then in a way, you can think of this whole picture, okay, linear attention plus the softmax is normal attention. If we have linear attention, as we increase this alpha, we generalize into intention. So intention is a superset of attention. And then in that bottom kernel, there's this thing called sigma intention, which is basically the same one as this one, but again, just with the softmax, just to mimic that exact relation between those. And we've implemented sigma attention as well. And it has very nice properties. It's very similar to intention, just like attention is very similar to linear attention. But this would be basically the whole space that we cover. And this is a picture that I like that summarizes the whole thing quite nice. If we think about the models that have these keys, values, and queries, and the space that is spanned by that, we can have this purple block, which is all the models of attention, or all the attention, all the sigma intention models, and a subset of that are actually our attention models as you basically drive this alpha to infinity. So this was a nice relation between attention and intention that was also mathematically grounded. That was really. I'm actually almost done. This is a short talk. Basically, there's a few last thoughts that I wanted to leave you with. This is, as I mentioned earlier, our initial criticisms that we heard from a lot of people is, okay, you're doing an inverse, surely that's going to be computationally super expensive. But that is not the case. We have a proof in the paper in case anyone is interested, that both attention and intention have the same computational complexity, which is this n squared d. So it's actually squared, not cubic. And on top of that, with intention, there's a lot of approximations that you can use for matrix inversion, which also speed it up a bit. We also ran some tests as well, because of course we can have the same computational complexity, but then be off by some factor that makes this whole thing unrealistic. And so we ran the same experiment with intention and with attention, and we looked at what's the slowdown factor. So how much slower is the intention than attention, and we get about twice. So this is okay. We were worried that this would be a scale exponentially or worse, but actually a twofold scaling factor, slowdown factor is not too bad. We also had a few issues when we were trying to implement this with the current system. So JAX is not very good for loops versus very good for parallelizing. So it was good for attention, but not so good for attention, and so on. But this seemed to be encouraging. And then finally, there's a lot of stuff that I haven't covered around variance of this model. If you think, when we're doing the classification, you can think of the equation basically as, okay, the queries, some measure of similarity, like the covariance basically, and the values are some labels. And depending what you use for this sigma and this y, you can get back different models. So you can insert there different ways of computing this covariance and these labels, and get back things, old school methods like LDA and QDA, which I'm sure some of you have heard. Maybe back in the day we heard about this in the masters. So there's different old school classification methods that you can get back just by replacing how to compute these middle terms. So this to us was also really cute, because it's another nod on like old school statistics that we can somehow bring back into our models and very easily exchange and run experiments. With this as well, what we did when we computed the covariance, we also applied kernel methods. So all of a sudden we didn't only have LDA, but we could have kernel LDA, and we could then project everything into kernel space within our deep network and back down, right? And then this allowed us also to scale up without having to make the network bigger, but rather just using smart kernel methods, which now seem ancient, but back in the day were actually quite useful. Right, so to close, TLDRs. Intention, which is the module that we introduced here, cannot be represented or approximated efficiently by our current attention models. However, we can implement it very easily with the current learning libraries. None of the computations that I showed you are difficult. Matrix multiplications we know how to do. Even inverse, most like JAX has like some inverse library, some library for inverses. We can stack them, so we can get the same behavior as we have with transformers, and we get informers. And finally, we proved through a number of experiments that they work on methods that people at least care about. I mean, real world is a big word, given that we've stayed relatively toyish. But the whole point of this paper was to show that it can work across a range of tasks. And we were not trying to scale up a big problem, but rather show what are the properties of the model in its simplest function. There's a lot of open questions, some of which we've thought about, some of which we're not. I have since moved on for this because a lot of us have been put on other projects at Google to make sure that we stay relevant. One could think about what other setups is this particularly useful for. As I mentioned, it is carrying out optimization as part of the forward pass at inference. This is why it was doing very well on some of these tasks, because some of these tasks benefit from having something that can just optimize or have closed form solution. It's like having access to an optimizer at test time, right? As long as you can project your problem into something that can be solved by least squares, you're done, right? Your model is going to compute that solution immediately. So it's just, yeah, projecting around that. So there are a lot of possibilities, and we thought about a few things here and there. What are their interesting computations? So we obviously introduced intention. This was one way to go. Be likely squares, I guess, but you could have many other computations that it's not just the attention or even intention. How can we combine keys, values, and queries in an interesting way to cover the space? Do we even want to cover the space? Maybe attention is all you need, right? So, but there is space for those questions. And then there's a question also around scaling up. We started a little bit medium easy. Some of the things were easy to do. Some people were wondering about language, and I think language is a bit of a special case because how the masking works. I don't know if anyone has worked with language, but when you train in batch and you're masking out the future, so you're not seeing what the rest of the sentence is. This is a bit harder to do when you're working with an inversion. But there has been since actually research from Google as well. I think it's that one actually. Yep. Who scaled it up and did it to applied it to large language tasks as well. So it's not impossible. It's obviously a rogue time to say like, hey, stop doing attention that's working so well and do something else. So it's not like anyone's going to pick this up immediately, but it was something I think that was a cute project that asked a few interesting questions that we were quite proud of. And I think with that, I'm done. If there's any questions, if they're very hard, send them to Wojtek. If there's any compliments or anything, send them to me. And yeah, that's it. Thank you, guys.
So we have some time for questions indeed. You work with fast. So...
I know Spanish people speak fast.
Yeah.
You find that the clients improve sample efficiency in some cases.
Sample efficiency for what?
Like, did it converge faster? Attention for the transformers?
Sometimes we saw that in one of the experiments, you could see that the curve got there faster. I don't know if we did any experiments where that benefit would be really clear. Yeah, you could imagine, you could have some sort of active sampling where you say like, oh, we know we can regress this function. Why don't we go and search more actively? We did not do that, but that's, yeah, let's add that to the list of future questions.
You kind of mentioned quickly about how maybe they're not so good at extrapolation, and I think one of the big things about attention-based models like transformers is their emergent properties. Did you at all look at that with intention? Or?
Yeah, so what we saw, actually, transformers explicitly or attention cannot extrapolate. They can interpolate, and it's proven but they cannot extrapolate. We have some experiments in the paper where we show that informers are better, intention is better at extrapolating. I didn't include them here, but that's a good question. We were showing they could guess outside of the range much better than attention, which is collapsing, and intention is actually able to do that. This particular example, when you haven't trained it at all, I think even attention would not know what's going on, right? Like it's after training, we have better, extrapolation properties. But yeah, there's a figure I think somewhere. Thank you.
So when you show the sketch of the different attention and intention mechanisms, it all started with the query key value triple at the bottom, and then they were connected in different ways, which makes me think, you said that maybe there are other gates that would work really, really well. And I remember that Google has had a precedent of recreating algorithms that do things which we already thought were doing properly, like matrix multiplication or sorting arrays, just by slapping another AI agent on it and trying to optimize how we do this algorithm. So do you think there could be a way
to train an agent or learn what a good gate for these intention, attention, super attention, whatever gates would be?
That's a really cool idea, actually. Yeah, you could try to imagine some sort of meta optimization. You're trying to almost like evolutionary algorithms where you're trying to see how do you optimize the computation inside. What you need for that, and I think this is not even clear for here, is what's the metric you would be optimizing against, right? And one of the things that I like mentioning here as well is we're not saying, oh, intention is better than attention. It really isn't. There's cases where attention is going to kick intention's butt. Like this is unquestionable. It's rather there's some problems where I think having this ability that intention brings helps you a bit more, right? So depending on what your task is, this answer would be different. So I guess the main challenge there would be, what's the metric? What do you want to optimize? What do you want your little new module to be good at? Do you have a good test bed for it? And then when you have that, you could imagine running some sort of Bayesian optimization or something where you do little changes. But yeah, I totally agree. There's also a world in which none of this is necessary because the transformers, actually, the way they are implemented is with self-attention, which is a bit cheeky because it means that keys, values, and queries are all the same. So it's not even like they're not even being treated specially or anything. You're just you're basically just allowing for these multiplicative interactions to happen and saying, I don't care how, you figure it out model, just by multiplication, I allow yourself to gate yourself and then do the best you can, right? So this is where there's a bit of search, but that could be a good way of searching that space. That's nice.
We have an online question here earlier.
Wait.
Miko was saying, real cool stuff. You have tested computational slowdown. I was wondering if there are any change with memory use.
Oh, okay. We have not looked at memory use. However, we did some experiments. I would not expect the memory use to be very different because parameter space is the same, and then the matrices that you are using you are doing an inverse, but you're still using the same space as when you have attention, right? In attention, you still have, as I showed you, this matrix of distances. So I would say, I've not proven this, but I would say they're. Yeah, sorry.
I was just curious, a lot of the equations kind of remind me of Gaussian processes. So I was curious if you have explored that connection so far.
We have not. What have we done that? So I originally worked on neural processes, which were inspired by Gaussian processes. So I've come from that kind of area. We have not really done much. The closest we've done to anything is also using kernels for a lot of the stuff. But we haven't. There's some research ongoing of people that are trying to build kernel methods into things like this, maybe into attention. It's not clear to me how that's going, but no, the answer. Yeah. Are you working on Gaussian processes?
No, not really. So that's why I was scared to ask the question, but the resemblance is there.
Yeah, no, for sure. There's.
Ask if experiments was the scaling factor, was it a learnable parameter, and if so, did it kind of converge to anything?
Interesting. We did make some experiments where it was learnable and we didn't find anything super interesting there. We usually just said we did a sweep. So it was mostly, more than anything, it was for numerical stability. I think we weren't at a point where we were playing around with that a lot, but it was just like, please, can we get this matrix to be invertible? And then that's what that was doing. That is an interesting research question, however, because in our ideal dreams that we've had all the time, we would have loved for it to be a function of the input as well, so the alpha, or a learnable function. So then you can say, okay, depending on how you see this context, you want to be more like attention or you want to be more like intention, right? And then you can drive that steering wheel that we did not get to. And we ran a few experiments and it didn't seem to do it out of the gate, so we moved to others. But yeah, it would be a dream if that was the case. Yeah.
David online says, thanks. Were there any other key query value models that you tried?
What did we try? Not particularly. So the thing is, I tell the story now like this because it is much easier to follow how we got there. But initially, I was coming from the optimization, and I was trying to see, can we get optimization into neural networks? And I looked at, okay, what are closed form solutions for optimizations? Because I don't want to have an optimizer in the loop. And this is the first one if you open the book about optimization. And so then from there, we actually then went into the whole attention. We never started with attention or transformers in our mind. We were coming from optimization. Yeah, so no, to answer your question. Hi.
When in transformers or informers, when you stack these blocks, right? You mentioned that you could change the coefficient in the calculation to get sort of a sliding scale between attention and intention. Have you tried that? Just like having a huge, like a transformer / informer model where you change that coefficient at different points in the.
Yeah, we have not, and that's a good question. It's very related also to what he was saying. Can you make this parameter? We haven't played loads with that parameter. We went a bit to the extremes, and like I said, we used it more for the stability. But that could be really cool. Yeah, we also thought of architectures where you could have it explicitly choose, do you want intention or you want attention, and then have that. But yeah, a lot of plans. And we're 2 people, which is rare for DeepMind. Usually there's 20 people on one paper. But this one was a small one.
Okay, Serwin asks, thanks for the interesting talk. I will be curious how matrix inverse operations scale. Is it computationally similar to attention for certain types of problems?
Yeah. So that's what I was trying to mention with this guy. There is people. It was quite unbelievable because at first we before we sat down and did the math, we wouldn't believe that they would be the same. But it computationally, that inversion scales the same as in attention. And the reason for this is something at a high level. Attention, yes, it's quadratic because you're having this covariance, but actually it's quadratic with a huge factor in front of it. So it's almost cubic, like, and this factor is similar to the size of the square matrix. So attention is surprisingly close to cubic, and intention can be rewritten if you're like taking the inverse can be rewritten as something that is quadratic with something else. So they end up actually, so intention is surprisingly low and attention is surprisingly high, I found, for my intuition at least. And we found that they actually meet in the middle. So the complexity, ended up being the same, which was everyone's first point of criticism. So we were quite glad that this came up with. I was mentioning to you earlier, it depends, however, then almost at a software like programming library level, because we found that with JAX, it was a bit harder to get, even though theoretically they should be the same. One is more parallelizable than the other, and JAX does better with parallelization than with for loops. So theoretically it should be the same, practically they weren't. So yeah, but we're not about to just change the whole.
Thank you. So I think it's good to stop here. Just before we wrap up, remember that if you like this kind of stuff, we have also a reading group running weekly here at Imperial. Feel free to ping me or to our email that we have on our website. Next talk, we don't have the title yet, but will be from Eugene Vinitsky from New York University / Apple on the 8th of April. So that's a Monday. It's good. He's traveling from New York just for that. So you have to forbid us to do it on a Monday instead. Hope to see many of you there. Thank you very much for coming, and let's have some sushi for those that are in person. Thank you, Marta.